So hello everybody. Today's tutorial is going to be about the recurrent graph neural networks model. So I will initially start by what we have seen so far about graph neural networks. Okay, so we have seen that in graph neural networks we want to combine the values of neighbor nodes, okay, into a meaningful representation for a target node. And how do we do it as it is now? We have seen how to do it usually using graph convolutions, okay, in which for these different distances of the neighborhood of a given node, we use a different neural network to obtain the neural representation for a node, okay? What is different from the convolutional perspective to the recurrent perspective? So basically, here you have two models, okay, two little schemes that represents how the new states are calculated for in a recurrent graph neural network and a convolutional graph neural network. So basically, in the recurrent neural network, we are going to see that the different step to produce the new embeddings for the nodes are going to happen with a neural network that has basically the same weights for each time step of the recursion. Whereas basically what we have seen so far is that with convolutional we use different neural networks for different neighbors depth. So basically here, if you consider k to be the neighbor's depth of one node, here you will have a convolution that happens far from the node, then closer and closer and closer. And for each time we do a convolution, we use a neural network which has some parameters. So basically, in the recurrent, we have that the convolution operation happens within the same parameter model, whereas with the convolutional neural network, the standard convolutional neural network, we're going to have different parameters for different steps, okay? So here, not to be confused, here t is our time steps, basically, because here we are not considering different distance neighbor. Here instead, k denotes the depth of the neighborhood to be considered. Okay, so now that we have seen this little introduction, I'm gonna go and talk about the graph neural network model and other variants, which are the gated graph neural network, to alleviate some of the problems that arise with the graph neural network model. So the graph neural network model, well, it's called very broadly neural network model because it was basically the first one. So it was a pioneering work that came out in 2009 in a paper from Scarselli and Marco Gori here from University of Siena. And basically these graph neural networks try to leverage the properties of recurrent networks for computing graph data, basically. Okay, so let's start by defining what are the components that we are gonna use for in our graph neural network model. So basically here we have I don't know, a target node for which we want to compute a new representation. We're gonna have as the ingredient the basically the states of the neighbor nodes, as we have seen in all other cases in graph convolutional networks. Then we're going to have also another component, which is the edge information, so the labels attached to the edges, okay? And we're going to also use the labels of the nodes themselves. So basically here we have that X is the state, okay, of the node. And then we have L, the L's basically for edges and 4 nodes, which are all they can be vectors. It is, let's say, the labels are preliminary information that we have basically on the graph. So, for instance, you can think about, well, the label of a node is just a characteristic of the node, but also, the label of the edges could be the strength of the connection, between the two, or some other spatial information that might be useful to predict the new states.
Sorry,
okay.
May I ask a question?
Sorry?
May I ask a question? Sorry to interrupt you. The label of the edges are scalar, so just one number, or it could be also a vector?
No, it could be also a vector. If you see here, I put it the RLE because it can be a vector of information, an arbitrary length. Okay.
Thank you.
I also have a question. So
yeah.
It's not clear to me what's the difference between X of the node and L of the node.
Well, basically, the X of the node is something that we will update during the diffusion process. So basically, it's something that is going to change, okay, during time. Whereas the label is something that's fixed.
So L is an information that is provided, so like a feature of the node, and X is a status that we use for our training, right?
Yes, exactly.
Okay, thank you.
You're welcome. Okay, just a little bit for the notation. We have the co of V, which represents the edges connected to a node, and the neighbor of V, which are the neighbor nodes of V. Okay, so as we have said, we have all the ingredients now to define our diffusion mechanism to compute the new representation for a node. So basically, here, as we were saying, so we have the new representation that we want to calculate, and in order to obtain this new representation, we use all the information that I've explained you earlier. So basically, the label of the node itself, the label of the edges attached to the node, the other states of the neighbors, okay, at the previous time t, and the labels attached to the neighbor nodes, okay? So this is a very general scheme, and of course in the paper they explain how to provide an implementation for this function. For now, we just see it in a general way, and then we will look when we go to the notebook, Jupyter notebook, how we can actually implement this function. So here we have our function that ideally computes the new states of the nodes. We also combine it with a readout or output function, okay, which is g of w, which basically takes an input the value of the state of a node at a time t, and its label, and produces an arbitrary output. So basically here, as always, this is the step to obtain a representation of the node, and here the output function is something that takes the representation of the node and gives us the desired output. So the output could be scalars or reals, depending on if it's a classification or regression problem, whatever. Okay, so these two functions, of course, are parameterizable. So the W that you see there are learnable parameters. Maybe it's not clear from the definition, but the parameters of the function f can definitely be different. I mean, they are different from the parameters of the function g. It's not that the W means the same shared parameters, okay? They are separated functions, but they are both learnable. So from now on, we will refer to f of w as the transition function, and g of w as the output function, okay?
Sorry, Giovanni.
Yes.
I have another question, sorry. In T0, xv correspond to the node feature? We will
come to that.
Okay, thank you. No spoiler.
Yeah, don't worry. That's why you will understand better what X means when we will go to the training phase. Okay, so something that has to be noted here is that whenever basically we compute a new representation from the node for a node, we use the very same function f. Okay, so again, differently from the convolution in which we aggregate the different neighborhoods, the different depths of neighborhoods with different networks. Here we have just one network that keeps basically diffusing the information among the nodes. Okay, so each node will have the very same function computing the state, the new state. Okay, why is it important? Because if we look at another perspective, basically this function creates an encoding what the authors describe as an encoding network, which basically is the unrolled network through the various time steps of the output and the transition network. So basically here, for instance, we have, I don't know, let's say that we have 4 timestamps. Okay, so this is the very first one. We will compute, so this is a network, let's say this encoding network is representing 4 different nodes. So basically it's a graph of 4 nodes. Okay, so for each node we will have the new state computed by f of w. Okay, each node will take in input this different information, and we will have, of course, the different time steps in which basically the different computation of f defines by themselves a new network, which is actually again the encoding network. Okay, so basically what we are saying here is that we propagate the information in the network several times, and then we perform the output. Okay, with the output function. The number of times we do this information propagation, we decided by fixing the time t. Okay, or in another slight different way, as we will see in a second. Okay, so nice. We have the function. We have understood how it works, how it works over time. But what is the real goal here? So the real goal will be to obtain a node state representation and an output value, which are basically unique. So we want to obtain a node state which is unique depending on the information of the nodes, of the neighbor nodes, and the topological structure of the graph. And also we want to obtain the correct prediction outputs from these node states. So basically what we want to do is to converge to a unique solution for both of them. There is a guarantee that we have given by the authors, which is if we manage to make f of w a contraction mapping, then we are sure that a unique solution exists. Okay, what does it really mean to be a contraction mapping? It means that through time, okay, the computation of the network will be able to produce representation that will not differ by let's say a certain constant. So here basically we are saying that the two vectors obtained at time t plus 1 and at time t should not differ too much. Their norm should not differ too much. How much? They should be less than this value epsilon. Of course, this is an arbitrary parameter, but we have we are sure that we can get there. How? So as I told you before, f of w can be and also g of w can be implemented in several different ways. The authors of the paper indicate that if you use a neural network, in order for this neural network to be a contraction mapping, you should add to the loss a penalty term, the term which is calculated on the Jacobian, okay, of the output function with respect to the weights. Okay, if you do this, you ensure your neural network to be a contraction mapping. And then this formula here, this solution here is unique. Okay, now we have seen what we need in order to obtain this unique solution. Now let's go to the main algorithm. How do we learn these functions? Okay, so this is the main representation of the main, let's say, loop. Let's have a quick look at it. So basically, of course, the first step, we initialize the weights, and we do a forward step in order to obtain the nodes of the state. So you were asking me what is actually X, the node states X, okay? Basically, they are vectors which are initialized to 0. I mean, because if the neural network is a contraction mapping, we will have this unique solution. It doesn't really matter from which point we start, we will always get there, okay? So basically what the authors say is initialize your vector to 0, and then perform what? Perform the forward, basically, step of the f of x, okay? Here it is represented with capital F, just because it's not for one single node, but it is for all the nodes of the graph, basically. So the forward step works like this. So basically, at each forward, we initialize this vector with zeros, and we train the function to produce these vectors, which have the characteristics to basically be very close after, closer basically than these parameters here, okay? Which is what we have said before. This we are sure to get to this point because F is a contraction mapping, okay?
Okay, so basically we learn that representation that starts from 0. Okay,
yes. Even if you start from 0. I mean, you can initialize them randomly or whatever.
Yeah, with random, with the normal distribution, but they should converge to the learned value.
Yeah. Let's also have a look at the backward step. So basically, here it is actually when we use the output function g of w. Okay, so we calculate the outputs, we calculate the loss, and then we calculate. I mean, this is a very complicated procedure to explain, but basically. To compute the gradient, the authors use what it is called Almeida-Pineda algorithm. Why is it useful? I mean, usually in recurrent neural networks, you would use the backpropagation through time algorithm, okay, to compute the gradient. The only problem is that with the backpropagation through time, you need to store the state of the node at each time step t here, okay? Whereas if you use this Almeida-Pineda algorithm, you don't really need to store all these intermediate values. You just need to store the final value, so this x of t here, and you still are able to obtain the gradient in order to update the parameters of the function and still the function be a contraction mapping, okay? So this is a little bit complicated, the algorithm. I'm not really sure I've understood it correctly, but still, this is the strategy that the authors used in this case. Okay, so basically we are done by describing the graph neural network model and in general how it works. Let's go and talk about some variants of the graph neural network model. So probably the most well-known variant of it is the gated graph neural network, okay, in which basically the transition functions and the output functions are the transition function is substituted by a gated recurrent unit. Okay, so we don't have anymore a simple feed-forward neural network for f of w, but now we have a gated recurrent unit. We fix the number of time steps instead of waiting for the solution to converge. And also, in this case, we, the authors in this paper used the back propagation through time, which is more costly. It costs more, but it allows you to. It allows you basically to. We will see later. We will see later. Okay, so basically here what you see is the new propagation model. So basically what the f of w function is doing. Okay, so here and we will see what this means precisely, but let's say that h1 of w is the initial state of the nodes, and then basically they are updated, the states, using the gates of a recurrent unit. So these are the reset gate, the forget gate, and basically it's the uses a gated recurrent unit to substitute f of w. So here there is something to note, which is this. So basically I have used x of v earlier in order to denote the node state. Okay, here the authors use h, so be aware that this x of v is not what we were seeing earlier. This is what we were seeing earlier. But here the authors also explain something different. So we were saying that with the graph neural network model, we need to initialize the state of the node to some value, and then we will let the algorithm to converge to a unique solution. So here we don't have, we're not sure that we're going to converge to a solution, but also the authors say, let's put some initial information that I have about the node into the node state. And this is basically what this node annotation means. Okay, so here, if you have some information, initial information about the node that you want to incorporate in your node state, you basically do it by concatenating the node annotation, so your initial values and, I don't know, a set of zeros, okay? So basically, yes, this is also to incorporate preliminary information. Okay, again, here we have another output function, which in this case is simply a neural network. Okay, and this is what the modifications to the previous algorithm that are present in the gated graph neural network. Okay, there is also another variant of this, which basically says, but what if we want to output a sequence of values from the graph, okay, while we are basically learning the node information, okay? So in this case, the authors also explain how to construct the gated graph sequence neural networks because they like short names, okay? So the idea here is, instead of producing one output after some time steps, why don't we use multiple gated graph neural networks in order to produce a sequence of outputs, okay? So in order to do so, they define the authors define these two functions, which are basically this f here and the fx and fo are two gated graph neural networks. Okay, so basically each one of these implement a transition and an output function, okay, as we have seen here. So basically, each one of the f implement this and this both, okay. And so basically, okay, f of x is the responsible for computing the new state of the nodes, okay. And f of o again is a gated recurrent unit. Sorry, a gated graph neural network which outputs the sequences. Visually, it is like this. So basically, here we start with an initial set of annotations, okay. We combine the annotations as we were seeing earlier with the zeros, and we obtain the states of the nodes, okay. We run the algorithm for some time steps, and then we produce a sequence, okay. I mean, we produce the output. Then basically what we do is we use a special output from this from here, from this f of x, in order to obtain another node state representations, basically combine it again to obtain the node states, and so on and so forth with the different time steps in the sequence, okay. So this is all from the theoretical side. Let's go to the tutorial and see how to implement this in Pytorch geometry. So first of all, I have to say that the graph neural network model I have here, it's not precisely what I've described, because I have not re-implemented this Almeida Pineda algorithm that I was talking about. So basically here is a little bit of a mix between backpropagation through time, and also I have not added the penalty that I was talking about, so the network is not forced to converge, because I did not add the penalty part, which is needed if you want the network to converge to a unique solution. So okay, so here let's do some imports and okay, so here I have chosen Cora just because it's a very light data set, so I can run it on my machine also. Okay, so let's see. Here I have created a class which is called Graph Neural Network Model, basically, okay? It extends message passing, which we have seen already. It is the base class for performing this propagation information and update of the nodes, okay? So let's start by seeing the components of the Graph Neural Network Model. So here, when I instantiate the network, I create also the states of the nodes. So that initialization that I was talking about earlier, basically. So here I've put zeros, but I could also put rand, for instance, in order to obtain basically a matrix that for each node has basically some dimensions, so basically some features for each node, okay? Here I guess I have chosen 32 or 64, we will see later, okay? So then we want to know how many basically classes, output channels we are going to need. So for Cora is 7 because it's a multi-class problem. We also set the epsilon, as we were seeing, which determines how good we want the contraction to be, okay? And also number of layers, which basically represents the number of layers in the encoding network. So basically how many time steps we follow in the recursion of the network, okay? And here we have implemented our two functions, the transition and the readout, by using this class, which is multi-layer perceptron. It's a very simple class that I've described here, and basically it takes several linear layers and put them together. It's very simple, very easy, very basic. Okay. So here we have all the components that we need. Let's go to the forward phase. Okay. So for each forward pass, we have seen that we have to collect the initial state of the nodes. Okay, so here we collect the node state that we have created here when initializing the class. Okay. And for a certain number of time steps, so here, again, since convergence is not enforced, I could not put like until convergence, but if I have implemented it correctly, I would have here until convergence. Okay, here I have said how many time steps. What do we do? Well, basically we do the propagation of the information, and this can be easily done by using the propagate function of the method passing class. So we don't really have to do any kind of string transformation in order to diffuse the information in the network. So once we have basically spread the information, we can use the transition functions to calculate the new states of the node. Okay. Here I have put something like stop if the convergence is reached, but it's not enforced. So basically, I guess we will hit this point very few times. Okay. Once we are done with the number of time steps that we want, we calculate the output function. The output given the node states. And also, since we are talking about a multi-class classification, we use a softmax for predicting the output. Okay. This is everything. I mean, this is what it was described in the graph neural network model, and here we have implemented it in this function. So let's try it out. Let's see. Okay, here I have to use it. Okay, so very briefly, okay, I've said create the initial states given the number of nodes in the dataset. The output of the readout function should be the number of classes. Then 32 is the dimension of the node states. Here represents the how many layers basically I will put in the transition and in the output function. So here I have chosen 5. 4 actually they will be. And also the epsilon for the convergence rate. Okay. Now I'm running it on my laptop, so I will run it just for 10 iterations because otherwise my laptop will probably fuse. Okay, so this is the model. So basically here, this first MLP is the transition function, which I've told you we have put several linear layers. Also, this is the output function, again several linear layers. With the output of 7 because of the classes. And so this is what regards the graph neural network model. Then we have the weighted graph neural network. So this is a type of convolution that it is already implemented in Pytorch geometrics. So I didn't have to do very much. Very similar to what we have seen in the previous one, but here we have substituted the forward model with a relational neural net. Gated recurrent unit. Yes, here it is. So our network in this time, our transition function will be this gated recurrent unit, and then we will process the output with another MLP, which is basically the output function, and then again we return the softmax. So here. Also, if you want to play a bit, you can execute it. Again, I guess I will stop it because otherwise my computer will explode. But here, yes. This is everything I had to say about recurrent graph neural networks. So if you have any question, I will be happy to reply.
Yeah, I have a question on the basic recurrent architecture that you. So the first one that you have shown.
Sorry, which one?
Really the first one, so the recurrent.
The graph neural network model, you mean?
No, the one, the recurrent, in the slide, yeah. Can you go back? Yes, let's say, not the first slide, but the first algorithm. So.
The first algorithm, okay.
Yeah. So it, if I understood correctly, it's not decided in advance how many iteration of the network you will have, right? So you run it until convergence. So until you find that condition, that norm condition is satisfied, right? So you don't have a control in advance on the number of iterations that are required to do that.
In theory, no, in the sense that in the paper they don't specify anything like this. So basically they say simply run it until convergence. I have found let's say a semi-official implementation which basically puts a maximum number of iterations limited. So I think if you want to stay strict to the paper, you shouldn't. So basically, this means also that the first iterations of the model, you will basically run it for a long time, because probably this convergence is going to be hard to reach at the very few steps of the training, during the first training steps. Later with the training, probably it will be easier and the convergence will happen sooner in time.
Okay. Because, I mean, in principle, it may take very long, because if you want to make sure that you reach a fixed point, I mean, I don't see why there should be a bound on the number of iterations in advance. So I was just curious to know if there is some hard limit. But yeah, I think you replied, so thank you.
The only reason is that maybe even if, but this is speculation, okay? So basically, even if you don't reach convergence, maybe you want to stop early because you can still compute this penalty term that you add to the loss function, and then maybe it will improve. I mean, it will allow the network to reach the convergence faster in some
to move in the right direction. Even.
I'm not sure.
Yeah. Okay. Thank you.
Oh, yes.
Yes.
Yeah, I also have a question. So a few slides before. Yes, I mean a few slides before, maybe. Yes, here. Yes. Okay. So about this graph, so you mean LA actually is a label, right?
Yes.
So the node label. So during your training, so your target is try to update the node to converge to the label value, or so your value as a node output, is it? So we can call it a supervised learning, as it, right? So you already have the label. So is it?
No, wait. Come again.
Yeah. So each node actually you have the label. So you can see a node A. So there's a label A, LA, right? So so in the supervised learning, so you try to update this node, so until this node will be generate the value LA, is it?
Wait, no, I mean, label of the node, it means actually whatever type of information that you want to include, okay?
So it's not the traditional the MLP. It's not the output, right? This is what you mean.
I think it's a feature vector in
It's not the
usual-
target variable, yes, it's the feature.
Yeah, it's the feature of the node and the feature of the edge.
Yes, exactly.
Oh, okay, I see. But XA is a feature of the node, right? XA.
XA is actually represents the node state, okay? The node state here, it is to be intended as a random vector, okay, that changes through time. The labels don't change through time.
Okay.
So I think X is the latent representation. So we want to learn a vector X.
Exactly.
We start from a random one or from 0, and through time we get this X of t+1. So at some point we converge to a final latent representation of the node.
Yes, exactly. And what do you put in the function that allows you to compute this new latent representation? Also information such as the labels, but the labels are fixed.
Oh, okay, I see. So I have another question is here. For your age, right? So do you also include the age or age features or age vector? So or you put age factor or this feature in LAF? Is it?
You mean the feature vector of a node or what?
A feature vector for the age.
For the age, you mean the...
So normally for graph neural network, you have the agency matrix, right? Then
Yes.
maybe you also will have the age features, right?
Yes.
Yeah. So this LAF is the age features.
Yes.
Oh, okay. I see.
Yes,
Thank
yes.
you.
Yes, exactly. LAF is the edge features, whereas LF is the node features. Sorry, the node. The node labels. Yes. I mean, yes. In this case, you can see LAF as the node. Sorry, as the edge features. Yes, basically. Yes. But they don't change through time. It is something that you already give to the input.
So just to recap, XV is the node hidden representation, and we have to learn. So we initialize to a vector of 0, 1 random values.
Yes.
LVU is the edge feature vector between node U and node V, and it belongs to dimension E, while LV is the feature vector and it belongs to n dimension. It has n dimension.
Yes.
It's correct. Okay.
Yes.
Okay.
Here L co of V, it means basically the labels of the edges attached to the nodes. So for instance, here
that it belongs to the neighborhood. Okay.
Yeah. Yes. Okay. I hope it was clear enough.
Yeah, now it's more clear. Yeah, thank you.
Okay.
Yeah, thank you.